Hello guys, this is the continuation of experiment number 2. Now we are in the part 2 of the experiment, which is the equilibrium also, which will be doing the rotational equilibrium. Okay, as was I mentioned a while ago, okay, equilibrium can be rotational and translational. So the first one we did on the first part is about translational equilibrium. Now this is more on rotational equilibrium. Okay, this is rotational equilibrium because if we're going to apply a certain force here, there will be rotation. So the target is to prevent the motion, the rotational motion. So for us to do that, okay, we need to apply a certain force also on the other side. So this is like a seesaw. If you're playing a seesaw and then you want to make the lever in equilibrium, okay, it should be balanced. Okay, so actually that is the meaning of equilibrium. It should be balanced. All the forces should be the same. So the forces acting here should balance on the forces acting on the other side. But in this case, we'll be using terms like torque. Okay, torque is simply the product of force applied to the multiplied the lever arm. Okay, so whatever be the distance from the applied force to the point of rotation, so that's the lever arm, and then let's just multiply the lever arm by the applied force. Okay, that is in terms of dyne or in newtons or in pound, and then that is the value of torque. So meaning torque is expressed in terms of Newton meter. Okay, so that's the unit for torque. Okay, according to the second law of or the rotational equilibrium, so the torque applied here should be equal to the torque on the other side for this to be in equilibrium. So we need to compute for the torque here, and then whatever be the torque here, that should be almost the same with the torque on the other side. Okay, so that's the target. Okay, so we'll be using the equal arm balance. So this is called the equal arm balance. And then we have the GLX, and then again we'll be using the force sensor. So the force sensor is used to measure the force to be applied on the equal arm balance. So the target is to put masses. Okay, I have here 100 gram. This is 200 gram to put on the right side of the equal arm balance, and then for the other side I'll be placing the force sensor. So let's start with the experiment. Okay. So as you can see on the table, there's we have 3 tables on part 2. Okay. So this is rotational equilibrium. The first table is about hanging mass. So that should be placed left side of the pivot point. Okay. So the left side will be this side. Okay, on your side. So that's the left side on your perspective, and then the second column is for the applied force. So we'll be using here 50 grams and 100 grams, and then as you can see, we have here loop 2, loop 3, loop 2, and loop 1. So where are those loops? Okay, so in the equal arm balance, so this is the center of the equal arm balance. From the center, this is the loop 1, loop 2, and loop 3. So this is the left side, your left side. Okay, loop 1, loop 2, loop 3. So we're going to put here the 50 grams or the 100. So this side is for the masses. Okay, this is used for the first table. On the second table, of course, this is the middle. This is the first loop, the second loop, the third loop. Okay, and then we'll be applying here putting here the force sensor. Okay, we have here on the second column, that's 50 grams. And then on the third column, we need to get the force in dyne. So since the given here is mass of the object, so we can compute the force by just getting the weight, the equivalent value of weight. So the formula to get the weight is simply mass, this masses, okay, multiplied by acceleration due to gravity. But since the given here is in grams, meaning we need to use the equivalent unit in terms of acceleration due to gravity. The same in the same system with grams, so that is 980 centimeter per second squared. So 50 grams times 980 centimeters squared, that's the value of F1. The same with the F2, so this is 100 times 980 centimeter per second squared, that will be the value of F1. Okay, R1 and theta 1 can be measured or can be computed. But what I did is I already computed for the value of theta 1 or theta and R1. So that is based on this illustration. Okay, so we have here the equal arm balance. Again, this is loop 1, loop 2, loop 3. On the other side, we have loop 1, loop 2, loop 3. For us to get the angle here, we need to compute for this length. Okay, so this is the adjacent side. This one is the opposite side. So if we're going to look at the equal arm balance and then measure the opposite side. So the opposite side is around 5.7. So that's 5.7 centimeters. Okay, and then the distance from between loops, okay, one loop to the second loop, that's also 5.7. Okay, so this one is 5.7 centimeters, this is also 5.7 centimeters. So if we're going to compute for the angle here, you just need to use the formula to get the angle. So the angle is simply arctangent. So this is arctangent, and then you have the opposite side over the adjacent side. And then for the hypotenuse, or for R, so this is the R, okay, in the equal arm balance, here is the R, this one, from the point of rotation to the loop, here's the R. Okay, we need to measure that, or to compute for that one. And then if this is the R, the angle here is the angle theta written in the manual. Okay, that's what we need to compute. And then for loop 2, this will be the R, here's the theta, and then for loop 3, from here to that point, that is the value of R, and then here's the angle. Okay, so based on the computation, if we're going to use this one, okay, this is 5.7, this is 5.7, this is the value of X, 5.7 square, this is also 5.7, so 5.7 square plus 5.7 square, square root of that, okay, so the answer will be 8.06. Okay, and then for the second loop, okay, so the adjacent is also 5.7, but the adjacent side will be twice of the 5.7, so that's equal to 5.7 times 2. Okay, and then for the third loop, that will be 5.7 times 3. Okay, just use this formula for the angle, and then we will arrive on these answers. Okay, for loop 1, the value of theta is 45, the value of R is 8.06. R here is the lever arm. Okay, for loop 2, angle theta is 26.57, then R is 12.75. For loop 3, 18.43, and then the value of R is 18.02. Okay, what we need to do later is just copy all the data and then place those data here in the table. Okay, I will be doing the first part, or the first trial. Okay, on the first trial, or on the first part, so this is 50 grams. According to the procedure, you need to put the 50 grams at loop 2. So here's the 50 grams. I'll be putting here at loop 2. Again, loop 1, loop 2. Now here is the 50 grams. Okay, as you can see guys, this is not balanced. This is not equilibrium. So we need to make the system in equilibrium by placing the force sensor on the other side. And then according to the procedure, here's the table for the force sensor. According to this one, okay, we need to put the force sensor at loop 2. So loop 1, and then we need to place here. Okay, and then the target is to balance the equal arm balance. Okay. So as much as possible, making sure that it should be okay in place. Okay, no movement. Okay, according to the rating, so that's 0.43, 0.40, 0.43. Okay, so that's 0.43. So the 0.43 is the reading on the here. So here's 0.43. Okay, here's the 0.43. Okay, let's compute for F1. Okay, again, the 0.43 is the tension, or the reading on the force sensor. So in this one, it should be placed, because this is in Newton. The 0.43 is Newton. Okay, we need to convert the Newton into dyne. Okay, So in every 1 Newton, that is equivalent to 100,000 dynes. Okay, that's the conversion of Newton to dyne. Okay, again, in 1 Newton, that's equivalent to 100,000 dynes. So meaning we need to multiply this by this one by 100,000 to get our reading here in terms of dyne. Okay, but before that, I'll be computing here per F1. Okay, so this is 50 grams. So to compute per F1, so that's simply 50 multiplied by 980. Okay, so that's 49,000. So the reading here is, the value here is 49,000. So that will be in dyne. Okay, R1 is, so we have here loop 2. Okay, let's look at the value of loop 2. So here's the loop 2. Okay, R is 12.75. So R1 is 12.75. And then the theta at loop 2 is 26.57. So here is 26.57. Okay, now for the second part, so this is loop 2. Okay, so this is also at loop 2. So loop 2 is also the same with the first table. So for loop 2, R is 12.75. And then theta 2 is, or the theta there is 26.57. Okay, now, so here's 0.43. We need to multiply that by 100,000. Again, because we need to convert Newton into dynes. Okay, so that's 0.43 multiplied by 100,000. Okay, the value is 43,000. So that's 43,000. Okay, then let's use the formula. Okay, for us to get the torque, again, the torque is equal to force multiplied by the lever arm. Okay, where this is equal to F multiplied by cosine theta multiplied by R. So this is the formula. So the F here is the F1 or the F2. And then the cosine theta is here's the theta. We need to get the cosine value of that. And then R is the R1 or R2. Okay, so meaning for the number 1, for us to get the torque, okay, that is simply F is 49,000. Okay, so this is the dynes. Okay, multiplied by cosine angle. The angle is 26.57. Okay, then multiplied by R1, which is 12.75. So this is 12.75. So the value of torque is 49,000 multiplied by cosine. So that's cosine 26.57. Okay, then multiplied by 12.75. 12.75. So the reading here is 558769. So this is 55769.25. So this is in terms of dyne centimeter. Okay, so here is the value for torque 1. Okay, this is 5. Again, the formula is F1 times R1 times cosine theta 1. Okay, so this 55769.25. Okay, the same thing with the second table. Okay, that will be F2 times R2 times cosine theta 2. So we have 43,000. Okay, then multiplied by 12.75. Then multiplied by cosine 26.27. So the answer is 490,348. So this is 490. And then we have 348.53. Okay, we just need to transfer the data torque 1, torque 2 on the third table. So this is 558,769.25. This one is 49,0348.53. Let's compute per percent error. Okay, here guys, the theoretical value here is the first table. Okay, the value of the hanging mass, the torque on the left side. So torque on the left side minus torque on the right side over torque on the left side multiplied by 100. So we have 558,769.25 minus 49,348.0348.53. Okay, divide by the theoretical value, which is torque 1, 558,769.25 12.25. Okay, the answer is this one. Okay, it's more than one. Okay, so that's 12.24. It's more than 10%. Okay, again, the target is to get 10% below. But for the sake of showing you how to perform the experiment, so this is the process. Okay, this is how to compute the data, and then this is also how to gather the data. So the percent error is 12.24. Now let's do the second one. Okay, for the second one, so here loop 3 should be the 100 grams should be placed at loop 3. Okay, I'll be removing this one, and then I will be placing the loop 3. So the 100 grams should be placed at loop 3. The 100 should be placed at loop 3, and then your port sensor should be placed at loop 1. So the port sensor should be placed at loop 1. Okay, then let's balance this one. I'm not very good in balancing, that's why we get a high percent error in. Okay, okay, that's why in doing the experiment, this should be done by group. Okay, because in my case, I'm the one reading the GLX. At the same time, I'm the one pulling the port sensor. It's not that easy. Okay, and then make sure that there's no movement. Okay, it should be straight line. Okay, if this is already balanced, just look at the GLX. So the reading on the GLX is 2.65, 2.71, 68. Okay, let's use 2.60 or 2.65. Or maybe 2.62. Okay, let's try 2.62. Okay, here this is 2.62. So 2.62, that is Newton multiplied by 100,000 to convert that to dynes to 162,000. Okay, and then this is loop 1. So let's look at the value for loop 1. Loop 1 R is 8.06. And then theta is 45. Okay, on the first table, this is loop 3. Okay, 100 grams is placed at loop 3. So loop 3 has R value, which is 18.02. Theta 18.43. Okay, now let's compute for the F1. F1 is simply 980 multiplied by 100. So this is 98,000. Okay, now let's compute for the torque. Okay, so that's just 98,000. 98,000 times 18.02, then multiplied by sine or cosine. So this cosine should be cosine 18.43. So the value is 167,5384.99. Okay, for the second table, 262,000 times 8.06 multiplied by cosine 45. Okay, the answer here is 14,149,3211.53. Okay, let's transfer the data from first table and second table to the third table. 167,5384.99. Then this one we have 14,93211.53. So the percent error is minus 167,538.99 all over 167,538.99. Ooh, my percent error is again more than 10. So that's 10.87%. Okay? So this is how to perform experiment number 2. Second part of which is the rotational equilibrium. Thank you so much.